Hello students, in this video we'll discuss the limiting behavior of effective nominal rates of interest as the number of compoundings goes to infinity. We recall that 1 plus the effective annual rate of interest is 1 plus the nth nominal rate of interest over n to the power of n. And what we'd like to do is figure out what's happening to in as n goes to infinity. So the first thing we're going to show is that if n is less than m, that this implies that in is bigger than im. So in other words, these nominal rates of interest are decreasing as the number of compoundings gets larger. So to this end, what we do is we're going to use some calculus. I'm going to replace this n with an x to put it in more of a standard calculus notation. And we can observe that if I look at ix, how we solve for ix, what we'll do is we'll raise this to the 1 over x power. We'll subtract 1 and multiply by x. I'm going to have x. And then I'm going to have the 1 plus I to the 1 over x. 1 plus I to the 1 over x. And then that's going to be subtracted from 1 minus 1. That's our function ix. I'd like to show the derivative of this function with respect to x is less than 0. That would show that the ix is decreasing as a function of x. And of course here, the x is what? The x is a number that's just going to be greater than 1. So that's something important. So here in our problem, x is going to be greater than 1. The number of compoundings is greater than 1 in our problem. Excellent. So what we'll do is take the derivative of this thing. So it's the derivative with respect to x of ix. Well, it's going to be the derivative of the first function, which is just 1 times the second function. 1 plus I to the 1 over x minus 1. Plus the first function times the derivative of the second function. The derivative of negative 1 is clearly 0. The derivative of I to some function of x is going to be 1 plus I to that same thing, times the derivative of 1 over x, which is negative 1 over x squared, and then times the natural log of 1 plus I. My objective is to show that this whole expression is less than 0. That's my goal, show that that's less than 0. What I'm going to do is I'm going to throw this 1 on the other side, though, and then factor out this 1 plus I to the 1 over x from both these terms over here. So if I do that, this is exactly equivalent to showing that 1 plus I to the 1 over x. If I pull that out of this term over here, I have a 1. So that's going to be a 1 from this. And then I throw this 1 on the other side, and then I pull that 1 out. So I'm going to have a negative 1 over x natural log, negative 1 over x natural log of 1 plus I. I'd like to show that's less than 1. Well, showing that this is by throwing this 1 on the other side of the inequality, so that's equivalent to what we're trying to do. Now, showing this is less than 1 is equivalent to showing that the logarithm of this thing is less than 0. So if I take the log of this, this is equivalent to the log of this first term over here is going to be a 1 over x natural log 1 plus I. And then plus the natural log of this messy term, 1 minus 1 over x natural log 1 plus I. I'd like to show that that's less than 0. That's equivalent to our function ix being decreasing. Great. Now, what we have over here is I'm going to call this whole value over here, I'm going to call that value just a y. So this is equivalent to showing that y is what? Now, of course, this thing over here is greater than 0. And of course, 1 over x is going to be less than 1 because x is bigger than 1. And then I have a y and then a plus natural log of 1 minus y. I want this to be less than 0. Okay. But this is equivalent to saying that the log of 1 minus y is less than negative y. And if I exponentiate both sides, that says that 1 plus 1 minus y is less than e to the negative y. Okay. And what we need to show now is we need to show that this is exactly equivalent to e to the negative y plus y minus 1 is bigger than 0. And of course, these are the first two terms in the Taylor expansion. So if I Taylor expand this out, this is certainly true. So that expression is true. That shows that our function in is decreasing as a function of n. So it's a decreasing function. So now I can find the limits. I know that there's going to be the monotone convergence theorem is going to imply there's going to be a limit of this thing. So let's compute it. So what we have over here is I need to find the limit as n goes to infinity of this expression over here. So let's do it. So I want to find the limit as n goes to infinity of in. And that is the limit as n goes to infinity of this expression over here. So that's going to be an n. And then I'm going to have a 1 plus I to the 1 over n minus 1. Of course, I have an infinity, and as n goes to infinity, this goes to 0, and this is going to go to 1, so I have 0 times infinity. This is an indeterminate form, so I'm going to have to write this as the limit as n goes to infinity of 1 plus I to the 1 over n minus 1 over 1 over n. Now I have the numerator is going to 0 and the denominator is going to 0, so I can use L'Hopital's rule. So by L'Hopital's rule, this will be equal to the limit as n goes to infinity of the derivative of the top, which is going to be a 1 plus I to the 1 over n times negative 1 over n squared times the natural log of 1 plus I. The derivative of 1 is clearly 0, and that's divided by negative 1 over n squared. And now as n, the negative 1 over n squared, these terms over here, this term over here, and this term over here are going to cancel out, right? As n goes to infinity, 1 over infinity is 0. 1 plus I to the power 0 is equal to 1. So this just converges to the natural log of 1 plus I. We know that that's the constant force of interest delta over here. So that's our value delta. And now what's the relationship between delta and I? The relationship between delta and I tells me that e to the delta, 1 plus I, is e to the delta, the constant force of interest. And now I know also that I n have to be bigger than this delta, so we get one more term in our global inequality. And so what is our global inequality? It says that I is bigger than I n. Now I n decreased to this number delta, so this is bigger than delta. Analogously, we can show that this delta n sequence of effective nominal rates of discount increases to delta. The exact same argument is going to show that. So that's a good exercise for you all. D to the power n bigger than d. So I have this string of relationships between the effective annual rate of interest, the effective annual rate of discount, the nominal rate of interest, the nominal rate of discount, and then the continuous force of interest, continuous constant force of interest, delta. Thank you very much.